But let's go through this week's lesson, and then at the end I could say a few words about the final assignment as well. So today we'll first go through how we can retrieve OpenStreetMap data, and then how we can analyze the road network. And based on these parts, then also, or these topics are then covered in the exercise. And as most of you came early, we did check that you were able to launch the instance. So I have, before the weekend, I created this extra blueprint. It's the same setup as in here, but it's not linked to the persistent storage. So this should be more stable, but it destroys all your work after 6 hours. So always commit to GitHub, but especially if you're working in here. So this has been kind of unfortunately not working as well as we were hoping to, but at the moment, at least today, it seemed to launch without any problems. But don't, a reminder that don't leave anything hanging in there. Always push your latest notebooks online after you stop working each time. And of course, some of you have then started to work with your own computers, which is nice. In the environment, under notebooks, lesson 3, we'll start with this retrieve OpenStreetMap data. Jupyter notebook, so now is the time to say if you have some problems finding this lesson's materials. Okay, so if there's no major issues, let's get started. So, well, yeah, OpenStreetMap is kind of my personal favorite topic. Maybe so, at least who of you all have been to these mapathons we have organized around Helsinki? Some of you, and then maybe overall, how many of you have ever edited the OpenStreetMap data? Okay, yeah, so quite a few of the present people. So OpenStreetMap, it's a map of the world, kind of similar to whatever we have, Google Maps, Here Maps, others, but it's open source. So it's a database with an open source license, and then you can use OpenStreetMap as a background as long as you give attribution to the data producers who are kind of, all of us can contribute to this map. And then, especially from Helsinki, the data is of quite high quality. We already used this data when we were doing geocoding. So if we search for Kumpula, it gives us the kind of area of Kumpula. Then we can search for Kumpula campus and such. And then if you would, I'll now just for showing. So if you would then sign up as a contributor, there's different tools for editing this database. But now I'm opening ID editor, which works in the browser. So you can see what is the actual data structure. So we have points, lines, and polygons. Sounds familiar. And then these different objects have different sorts of attributes. So here is, well, that's Dynamicon. We are now sitting in Physicum building. So it's a polygon object. It has a name. It has an address. We could add opening hours, whatever. So you can then go here, edit the geometries, edit the attributes of these different kinds of objects. And today we will learn how we can fetch these geometries and attributes to Python using a package called the OSMnx. So the great thing about this data is that it's then similarly available globally. And of course, if it's not available from some place, we can just go and add and edit it. So what we have done in these mapathons is that there's some areas that, for example, Doctors Without Borders or Red Cross is going to do, for example, a vaccination campaign, or there has been an earthquake and there is no openly available digital data, and then people activate, go and edit roads, buildings, waterways, residential areas, and so on to OpenStreetMap, so that then those can be analyzed and used for decision-making purposes, for example. So this as a quick introduction to OpenStreetMap data. For example, then the route planner Reittiopas in Helsinki uses OpenStreetMap data as the basis of the network analysis. So for example, if you take a route from here to your home, how you walk from the building to the bus stop is based on OpenStreetMap street network. Then there's some other data added from the traffic timetables and such. Okay, but we could talk about OpenStreetMap for the whole day, but how we will then interact with this data base is then a Python package called OSMnx. Let's see where this link leads me to. So in the email I sent you, I asked you to check a YouTube video where Henrik is interviewing Geoff Boying, who is the developer of this package. So if you didn't yet watch it, do watch it. But basically, what this package does is that you can download kind of administrative area polygons, like now we saw this Kumpula area, so you can download these areas, and then from specified areas or regions you can download the street network data for network analysis purposes. You can nowadays also download, for example, building footprints, land cover polygons, whatever types of data you have in OpenStreetMap. And then OSMnx has some capabilities for fixing the network topology, which is then important when doing the routing. And then there's some tools for analyzing the network together with another package called NetworkX. And just as a curiosity, we can see that also kind of the main developer of this course, Henrik, has been quite active in contributing features to OSMnx. So most of these packages we are using, they're developed by people for their research purposes, and then they put them online. Other people start contributing. So it's quite a nice discussion that Geoff and Henkka have in that other YouTube video. So Geoff explains how he has developed this package for his research. So he's a professor, assistant professor related to urban studies. So you can do analysis related to urban design and transport network analysis with this package. There we go. Yep. So here's also the link to the video. It's 25 minutes, so we won't watch it now, but do watch it maybe before doing this week's exercise. And there's also a scientific article published in Computers, Environment and Urban Systems where Geoff has explained the tool, the main features, and how it can be used for transport analysis purposes. So the main point here is to make kind of, he has provided a tool for doing consistent, repeatable network analysis, as for example, kind of data accessibility or accessing data that can be analyzed using similar metrics has been a challenge so far, if you think of urban analysis on a global scale. How many of you did watch the video? You don't have to have watched it, but well, nobody. Okay, maybe I'll then won't show the whole thing, but I'll just kind of show some flashy maps. For example, let's check from here. So already from these data have been fetched with OSMnx. And already by looking at them, you can see that the structure orientation is different in different cities. And then, where is it? Well, here is the nodes, kind of nodes from San Francisco, colored based on topology, or elevation. So you can also, it's Google, elevation data based on Google API. You can also fetch that. And then there's some packages for doing these kind of like, well, urban design or kind of urban structure metrics of the orientation of the road network in different cities. And then of course all the layers of the urban planning affect the way in which the urban structure has emerged or been designed. So these kinds of things are the nice plots we won't cover today, but some students last year applied these in the final assignment, so just as a motivation. Yep, okay, so let's get started. If you have the notebooks open from this part. So we'll start, of course, by importing the modules that we need. OSMnx as OX. So with OSMnx, at least how Henkka has instructed, so we can import it with this shortened alias OX. If you're working on your own computer, you probably need to install this package, and when you install this package, it also installs Network X that we will use in the second part of the lesson. Yep, we'll start with that, and let's see what other packages we need later on. And well, we want to fetch some data, so in this lesson we have no input data, we'll just fetch everything online. So in the tutorial we have used Kamppi as the area of interest, so let's use that. So we can start by specifying a string. Oops. What is it? String with a place name. Here you need to, now with this Kamppi, Finland. With Kamppi, I already know that this kind of query will work, but if you would be starting with some new area, how would you know that is this a valid place name or such? So you would go to nominatim. I'll just show this. The nominatim interface. So this is the same geocoder that we used. Was it week 3? And we can just test with some short queries if they return something that is actually makes sense. And let's hope my internet works. So now if I search for Kamppi, Helsinki, Finland, you can see that it also refers to, there's, for example, the Kamppi metro station and such, but there is a polygon related to this place name, and that's the one that we will be interacting with. And where we are actually then getting the data from is an API, or an application programming interface called Overpass API, which is one way of fetching OpenStreetMap data. I'll show this later how it works, but basically we are using Overpass API then for actually fetching the data. Moving on, we'll start with fetching the actual street network, as that is the kind of end goal of today, to analyze the street network, and let's call it graph. There I might have to restart my browser, and in OSMnx kind of the core functionality is to fetch graph from place, and we could also, there's other related methods for fetching graph from address or graph from point, but now we're using this kind of place name query to start with, and then we can give the place name as input in there. And then I have a typo. So you can run that. Let's see that everybody gets the data, and while we're waiting, I'll open up a new browser window because that's getting a bit slow. Okay, if you got the data, you can already start exploring a bit what we have in there. So let's just wait. Maybe we'll leave those running and I'll explain a bit what we are actually doing in here. So first of all, we're using this OSMnx graph from place function. And here, again, it's good to just, well, read the docs. So go to the documentation and understand. So this is, again, a kind of high-level package which makes it easy for us to do the end analysis, but it might be a bit hidden what is actually going on in there. So the method was called graph from place. So you can see that there's graph from address, graph from bounding box, graph from file, graph from place. So this is the one that we are using at the moment. There's again a bunch of parameters we could define, but basically I guess the query string is the only one that we need to pass. And then there's always, if there's a parameter equals to some default argument, so then that's the default setting that is used. So we are now fetching all private network pieces of a network, and then there's a bunch of other parameters, but the place name that we passed is the string, query string for the places that are then geocoded, and from that place then the data is downloaded from. So we are now querying a network dataset from this Kamppi Helsinki area. And once we get the output, it will be a directed graph, and once this will run, it will return that it's a network X class multi-graph. So let's also check what is that about while we are hoping that the outputs finally return something. So then here we notice that OSMnx is using this network X package that we'll use in the second tutorial, and there is an object type which is multi-graph, which is basically for storing graphs. So what is a graph? We have some nodes. So if you think of the street network, this could be a junction, for example, like this, and there can be some junctions with multiple directions. So we have some nodes, and then we have some edges. So that's the vocabulary in a graph. And then often they are also directed, so there can be then, you can either go two ways or one way, and so on. So then we go into this kind of network world. And if you have taken or will take some of these computer science courses, so then it's kind of a different world to design these or implement these algorithms for finding the shortest paths in a network, or calculating distances and finding specific nodes and calculating these network statistics. One way to make the query less heavy would be to then specify, this would have come later in the lesson, but we have this, let's see, from place. So there's this network type parameter. So if you're not getting a response, you could type in network type equals to drive, which then will only take, it will filter out some types of roads from the network and only focus on specific types. So I'll continue with this smaller graph. You can, if you didn't have to do this, so that's fine. Graph. Okay, so we have yet another data structure here. We have had GeoDataFrames, GeoSeries, data frames and such, but now we have a network X graph data type. And then, yeah, as I mentioned, then in the second part of the lesson, we'll apply some shortest path algorithms on then this network. But let's continue with the very basics. And often a good next step is to just visualize the data. So there is in OSMnx, there is a method called plot graph for the graph. So you can run that, and then it visualizes our network, so you can see a bit transparent these dots. So they are the nodes, and then we have the edges, so the lines. So if you would go and edit OpenStreetMap each time you create this node, then it actually goes into the database as a point. And then in case this is one road, here's a junction, it goes here. And then if this is another road, even if they would go on top of each other, but there is no node, we always keep reminding people to make these routable networks. So without the node, there is no junction, so there is then no way to turn from here. So that's then a data quality issue that you might encounter sometimes when using these crowdsourced data sets. Moving on, we already discussed the place item, but there is then in OSMnx, there is a function called GDF, which stands for GeoDataFrame from place. And we had this place query stored in the variable place name. You can just run that and test it, and I'll store that in a variable called area. And as the name of the method tells us, we actually get now a pandas, GeoPandas GeoDataFrame, which we are familiar with. And then, as I already quickly plotted, so it has one row of data. There's a polygon geometry in the geometry column. It has the place name, then bounding box coordinates generated by this function. And then we can plot the area using matplotlib just to see. So it's now still in this VGS84 coordinate system, so that's why it looks a bit weird, but this is roughly the same polygon that we saw in this nominatim API when we search for Kamppi. And based on this area, we then fetched the network. Right. Furthermore, we can fetch other types of objects from OpenStreetMap using OSMnx. So there is ox.footprints from place. So if you have watched this lesson before or used OSMnx before, so it used to be buildings from place method in a previous version of OSMnx. Now it has been updated so that we can also fetch other types of footprints, such as parks or forests and such. And I have an example of fetching parks at the end of this document. And again, we give the place definition in there, store that in a variable. Might take a bit more time than fetching the polygon because, well, it's not a big area, but Kamppi is full of buildings, so we can expect to have quite a few buildings. So I'll start before printing out the data. I'll check the length of the data frame, which is 427. So there's 427 building polygons in this data now. So let's not print them all, just the few first ones. I now took head 3. So you can see that there's some index, then there's nodes, then there's geometry. So all of these are polygon geometries. Then there is a bunch of attributes, quite a few. So then all of these column names depend on the attributes that have been added to these features on OpenStreetMap. And as those of you who have edited OpenStreetMap before, you know that you can also add new attribute types, so you could add new columns to this data set when editing the data. So there's different types of addresses, Most of these don't have any, but we can see that the first one has some name in Korean, for example. So if somebody knows Korean, so you can translate that. But Lasipalatsi is, for example, one of those buildings in our dataset now. Maybe as a quick addition, those of you who haven't been so much editing OpenStreetMap, so we have the geometry, so points, lines, or polygons, and then we can add these tags. So if in the humanitarian mapathons, we often add building equals yes, that this polygon is a building. Or we could add building equals school, so this is a school building. So each tag always has a key. So the key would be then building, and then value is yes, or value is school. So there are these key value pairs, which are the tags. And then this OpenStreetMap wiki contains descriptions and discussions related to all of these tags. So then especially this highway tag is quite relevant when analyzing street networks. And it's good to know a bit the local context when fetching data from OpenStreetMap. And then if needed, you can also go and improve the quality of the data. So let's check buildings.columns. Well, we could also check how many columns. I'll just quickly check. So there's 93 columns in there, which is quite a lot. And then also some of these columns might kind of contain the same information, so it's not always super harmonized. But just as a starting point, there's even suojelumerkintä, which is in Finnish and probably refers to if the building is somehow protected. Then the next object type, points of interest, so POI is often a kind of acronym for that. So this is, I think this is a feature Henrik has been adding to this package. So this OSMnx poise from place again takes this place string query as an input, and then we can filter the result based on this amenity tag. So again, then there's a link to this OpenStreetMap wiki for all the possible amenity types, such as restaurants or maybe even public toilets. Whatever you have, you could then fetch based on this this attribute. So in this example, we could fetch restaurants. OSMnx.poise from place. And then we have this place name string, and then amenities. So this could be a list, or it has, I think it has to be a list, but we're only now fetching restaurants. Let's try that. I'll create a new cell in here, and again you can check. Oops. Place restaurants. Am I making typos in here? No. Restaurant is the, yeah. So the tag is restaurant, of course, because we have then only one restaurant. We are getting restaurants. So there should be more than 0. Okay, 212 restaurants in this rather small Kamppi area. Again, you can check the columns. So there's again quite a few. I'll just check how many. 79, so not as many columns as in the buildings dataset, but still a lot. And then in the next code cell, just to save some time, so there's a list of selected columns, and then we could filter the restaurants, so brackets and then a list of columns, so then we subset the data. You can check that on the fly. So again, there's an ID for each object, name, Kabuki, Atelier Finne, Empire Plaza, Hampton Bay, Ravintola Pääposti, and so on. Opening hours, so this is for example a feature we could now go and add to OpenStreetMap, address, so forth. So then based on these, if you were making an interactive map of restaurant opening hours in Helsinki, you could move forward. Okay, then moving on with introducing these useful OSMnx functions. So then you remember that all these other responses have been now GeoDataFrames, but then the first one was this weird graph object. So then we can't interact with it as we have used to be interacting with spatial objects which are in GeoDataFrames. So then luckily there is this ox.graph to GDFS function. So notice there is now GeoDataFrames. And as I quickly explained, always a graph consists of the nodes and the edges. So then this function will actually return 2 GeoDataFrames. So as an input parameter, we give the graph that we fetched earlier, which was taking too long time. And then as an output, we will get 2. So that function will return 2 values in this order, nodes and edges. So you can run that. Graph. And then we can check first the nodes. So you can see there's Y, X, OSM ID, some tag information, and then the point geometry. So these are now the nodes in this road network from Kamppi. And then we have these edges, which are then, there's again some attribute information. I'll just print a few rows. And then you can see that the geometry type is line string, so the edges are the lines. Now as a GeoDataFrame, and then we could do all the GeoDataFrame stuff to this object. And you can see, for example, highway primary, so now I have only the drivable network in here as I put that parameter in there. Yep, so then there's just this note that now we have been using this Kamppi polygon, so you can also pass a point with a buffer or some existing polygon, for example, but here we're first passing the query, it gets geocoded, and then we fetch the data from there. So there's quite good tutorials on the OSMnx GitHub repository. Also watch Geoff's video and then read the documentation. So then it depends a bit on the workflow, how you start collecting the data. And indeed, as they discuss it quite nicely in the interview video, but if we would be then fetching street network data for the whole of Finland, it indeed then kind of behind the hood breaks the query into smaller pieces and then puts them together on your computer. So then of course the larger the area, then the longer the query will take, but should in theory work. But then there's like, if you want the OpenStreetMap data for the whole world and all the possible tags, so then OSMnx is maybe not the best option. So then there's also this, so here you have these kind of data dumps. So not from the API, but actually data dumps of different continents or the whole world, on top of which you could then build your pipeline as well. So maybe OSMnx is best if you are interested in the street network or specific types of tags, maybe from a restricted area or then cities, countries scale. But then indeed, if you want the whole data dump, then go to GeoFabric and download from there. Okay, so finally now we have all these layers. So let's plot them to first of all verify that we have fetched the correct data, and then they align and we have everything we need. So a bit refreshing what we learned last week. So at this point we have in memory a variable called area, then we have the edges, the nodes, and then buildings and the restaurants. And if you use the same variable names as I did, you can just repeat these. So we can plot the area, and here there was readily available this figure and axis object, so we can plot to that object, so we get everything in the same figure. And the default color is always blue, so we can then change using for the polygon objects the face color, for example, equals black. I'll just use the same as we did in the online tutorial. Then the street edges, dot plot again to the same subplot. We have nice blue lines. We can reduce line width equals 1. I don't know if it reduced anything. Do this, do that. Then the buildings plot again AX equals AX, and there can again change the color, and then there was this alpha parameter that ranges from 0 to 1, so we can add a bit of transparency. So there seems to be a few building polygons on top of each other where they become brighter, and then finally the restaurants plot AX equals AX. Dumps could put color, put red, show nicely, and maybe reducing the marker size. What do we have? 10. I'll scroll up a bit. So there are still all these data are you haven't really checked it, but they are in VGS84. We'll reproject them soon. I'll just quickly remind you. So there are these like pre-named colors. I linked this page to the Slack channel where you can then check these possible predefined colors, or then you can use these color codes also. Okay, so that's kind of the basic pipeline for fetching the data, and then next we'll move on to analyzing the street network. So we can finalize this. Is it okay to continue, or you still typing? Yeah.
About the restaurants.
Yeah.
Why didn't they all appear in the footprint, or like the overall area of Cologne? Like some of them were kind of hanging out outside of the...
Yeah, so I don't know the specific details, but I guess that you can see that this is the actual kind of footprint of Comfy, but these kind of extend to the bounding box. So my first guess would be that the restaurant, we had the query Comfy when fetching the restaurants, but we have also restaurants kind of outside the exact footprint of Comfy. Tell me if I'm wrong, but I think that it would be then kind of from the bounding box of the Comfy area, or something like that, where the restaurants have been fetched. So they're kind of, and now because the projection is it's not a projected coordinate system, so they look a bit like they're popping out from the image. Yep. So then I had a little section here. There's also tools in OSMnx to on the fly reproject the data, but we could just to kind of recap the core stuff from this lesson. So we have this PyPro CRS class. And let's say we would want to then reproject these coordinates to some CRS that makes sense in Finland, such as 3067. So we could do that. So there was this CRS from EPSG function, where if we know the number, we can give that as a parameter and store it. That works. And then we have all these layers: area, edges, buildings, restaurants. So if I start with area equals area to CRS, and then this projection. So I'll do that, then I copy and paste this, is it 4 times, then I have edges, nodes, restaurants, missing the buildings. And then the buildings, okay, so then what I could then do basically, just to copy paste the same thing, of course would be nice to have a function for doing all of this replot, so then it looks a bit nicer in the correct kind of more adequate projection. So scroll back up here. In the meanwhile, I can change the colors just for the fun of it. What did we have? I had edges. So if you change the color of lines, then it's not face color, it's edged color, and also of course in a polygon you can have edged color. But this is now just to allow you some time to do the stuff. Buildings. Let's see. Something like this. So is this pretty much clear? As I said in the beginning, OSMnx is useful for fetching these area of interest polygons, then downloading and constructing street networks. We have now downloaded the street network. We'll move on to analyzing it soon. And then also we'll learn how to save. Well, now we could save these to file, these GeoDataFrames as well, to do then some further analysis. So this is now mainly just for base map plotting purposes. So I think we could have a break soon. There is a little task. If you're super eager, you could try. So the main functions we went through was this, well, GDF from place for fetching the area, then GDF from graph from place for fetching the street network. I used the network type drive to filter out other types of roads, and then converted this GDF to edges and nodes using this graph to GDFs. Then we fetched building footprints. And indeed, here's again note about this network type drive, which should be in hyphens like that. So if you don't want to have a break, you can test these from, let's say, I don't recommend trying to fetch the graph from the whole of Finland, but maybe I tried Vantaa yesterday and it worked quite nicely. I'll just quickly show this, how to fetch other types of features. So we have this footprints from place function, and we have still the place name, and then this footprints from place. I'll just show the documentation quickly. Footprints from place. So there is this footprint type equals building. So that's what we did. The default value is building in there. But then if you see the parameter documentation for footprint type, it says the type of footprint to be downloaded OSM tag key. So you remember these tags were the key and value pairs. So we can have building equals yes or land use equals something. So whatever these tags exist, we can fetch those footprints. And then in this example that I have in here, I'm interested in parks. And the convention to tag at least urban parks is tag key leisure equals park. There's also other types of tags, such as land use recreation ground or land use grass and so forth. And for the central park in Helsinki, you should use probably forest equals true or land use equals forest. We can check that. But we then first fetch all the types from this place that match the tag key leisure. And then you get some data. You see that then there's a column called leisure and there's park, park, park. But then if we want to see all the values in one column to check that we only have parks, there's this value counts function, which is quite handy in many situations, also for checking if you have no data in some of the columns. So then we see that we have 15 polygons that have the value park, but then there's also pitch for some like playing some game. There's 2 dog parks, marina, flower bed. So we could of course go and check what all those are, but here I'm then selecting from this leisure data frame based on the column leisure those values that are in this list. So this DataFrame.isIn list returns true and false values, and then I pass that to the data frame, and then it picks all the rows where the value was true in this condition. Run that. So then from this Kamppi area, then I have all the parks, and I could then add those to the original map. So with this same logic, you could then pick other types of land uses, leisure types, whatever footprints there are in OpenStreetMap from any area in the world, basically. So let's have a break. If you don't mind, let's try to come back. Well, let's have a 15-minute break, so 35 to continue with the network analysis. And if you're bored in the meanwhile, you can test this data fetching from a different area.